Okay, so this is the module 2 of lecture 19 in our 4774 machine learning like fall semester class. And so in the module 1, I roughly explained why we designed that deep learning nutshell in this module 2, and now we move to the second variable that we can use it to decompose the deep learning literature or the works. So in this second variable, and then we talk about like we're introducing a few new tasks or the tasks that we haven't covered much in all of the sessions we have covered so far. So in all of the sessions we covered so far, we focused on regression and classification, but the trends I selected in this smaller module is the 3 different tasks. So the first task is this generation task. The very classic popular work is the DeepFake. And the second type is deep reinforcement learning. Very classic current application is this AlphaGo, AlphaZero, or the game agent. And then the third task we are going to talk very briefly here is this learning to learn, meta learning. And then the few shots or zero shot recent very popular tasks are just like a subtask here. Or even more general, this learning to learn can be think about more like a path to this general intelligence tasks. All right, so let's get started. So this first possible task, like we select into the trend survey, is deep generative tasks, deep generative modeling. And we can use this from Ian Goodfellow. He kind of decomposed the research landscape of generative models into latent variable model based, like a VAE model, or implicit model based, like a GAN model we're going to talk about later, or like a transformation based model, and also this autoregressive based model. So if you're interested, feel free to check out his, he had a few like very good survey talks. And then, so the first top question is why generative models? Because generative models provide excellent test of ability to use high dimensional complicated probability distribution, and also this simulating possible samples, and can hopefully be helpful for the future planning, and also it can like just like impute the missing data. And it's also this, there are many realistic generation tasks. For example, this using style to like style transfer about the artist's work, and we're going to see a few like in the next few slides, the realistic generation tasks and applications. So for example, you have this images are not as quality as you like, and you can use generative models to try to improve its resolution, improve its quality, and see, look, if there's a problem, like actually here, if using different type of generative models can in fact make this imputation really well. Make this recovered image looks really nice quality. And the other type of generation task can be, so everything we cover so far is like given an image, you predict a label. So is there a dog there, is there a cat there, whatever. So this is kind of reversed input and output. So rather than giving the image as input, we can give you the input is the segmentation segmentation, just a segmentation plot. And can you use that to generate very realistic images? I mean, for example, this is like pedestrian passing the street, or the buildings generation. And this is actually it's already old, like 2017 CVPR paper. The current this type of label to image generation are actually much more like promising and then look better than this. And also like this kind of edge to image generation. For example, you have the sketches of the like the bags, or like designer just write the sketches, then you actually can use this kind of generation to generate many different kind of images, and then follow, as long as it follow that kind of sketch the designer generated. And this really opens this whole door of production, if you think about it, or design. Yeah, so this is also a very interesting task. And the other is, so we used to have just image input, we try to generate the captions, but you can just flip it, right? You can have the text input try to generate the images. And the very kind of popular task, I mean, in this generation category, is this called DeepFake, and it has been used to generate really, really nice quality face. I mean, these like this people's talking videos. I mean, then and then you try to, one person talk, you try to fake it into another person talking, and there are many variations of this, like face swap, puppet master, or lip syncing, and then this has been used bad use on a few cases. Maybe you already know from the news, but people also start to use them for the good impact. For example, Facebook using this to doing anonymize the face videos, those faces in videos, right? And this looks really real. If you look at that, I mean, you cannot even tell this is a fake face. And the other possible application is you can use this DeepFake lab, like a really great toolbox, to de-age, and this, which is really a very hard task previously using Photoshop, and now like it's just a simple library application. And it's enormously powerful, but of course it's also enormously dangerous. So there's a lot of current efforts trying to detect those images that are generated by these deepfake technologies. And so this is like a list of deepfake history. Feel free to check out, and they're mostly, yeah, so feel free, they're just two, we have a short session, so I will not jump into each, but feel free to read carefully and then check out each papers and to understand how this really fascinating tool grows from the small ideas until now. Okay, so that's these first interesting tasks, generation, beyond what we covered, the regression and classification. And the next interesting task is this is actually reinforcement learning task. And deep learning recently gave really a new life to the reinforcement learning. And this was kind of ranked by MIT Technology Review as the 10 breakthrough technology in 2017. So what is reinforcement learning? So it's really just trying to learn this agent can interact with an environment and without this very clear labels. And agent interact with the environment and learns by maximizing a kind of reward signals. And the reward signals are much less supervised compared to those kind of labels we normally have in the supervised tasks. And so to summarize the reinforcement learning, there are two really important challenges in the reinforcement learning formulation. So first is the supervised signals. It's a much sparse and less supervised signal. And then the second type is, so your data samples are not just IID anymore, are not IID. Or everything we have covered before have this IID assumption, right? But in the reinforcement learning, your samples are the consequences of the agent interact with the environments, right? For example, the whatever you observe, it's dependent not just on the current state of where you are or whatever state variable. It also dependent on what this agent, the action just taken before the current. So there's a very important like distribution shift issues there too. So which makes reinforcement learning kind of a difficult task. It's a much more difficult task compared to supervised setting. So deep reinforcement learning, essentially we can think about is try to like using deep learning, this deep neural network functions, trying to kind of like formulate to learn. There are many different ways to use a deep learning function inside this reinforcement learning loop. So for example, you can use it to model these model this using this observation and reward as input, and then action as the output. So more like a policy to using this observation and current reward to predict what action should I take. So this is one kind of deep reinforcement learning. There are many other kinds. What really created this popular of reinforcement learning, or is the start of the deep reinforcement learning, is this very important work called AlphaGo. And the AlphaGo combines the supervised learning and reinforcement learning to learn the search directions in this Monte Carlo tree search, and trying to have this computer-based gaming agent to play the Go game, which is a very difficult game because the search space is it's much larger compared to previous game that computers are good at. So feel free to check out the details. I will not talk about it here. So there's a classic idea proposed in this AlphaGo is this policy network and also the value network. So there are two networks here, both relied upon a deep neural network based formulation. It's actually convolutional neural network based formulation more specifically. And then one step further from AlphaGo is something some work called AfterZero. So there are actually two computer agents trying to self-play with each other, trying to learn better functions that can give guidance to the agent about what is the next move to pick. And this graph actually shows you this AlphaZero formulation is really just converges super fast to a better performance to the previous baselines. And then let's look at this Go on this lower row. Lower row is the Go game, which is AlphaGo, and then you can tell the AlphaZero is the blue curve, right? So just with self-play like 1,000 steps, and AlphaZero without using this human, because AlphaGo was trained by the previous masters, human masters history, but the AlphaZero is not. AlphaZero just learned all those from the self-play, but AlphaZero converges really quickly and reaches the performance of AlphaGo, and then which is another super big breakthrough because you don't need this supervision from the previous masters. You can just self-play in this type of gaming setting to learn a better policy. Reinforcement learning is a huge and complex field, and so the OpenAI has this spinning up website, which it's just almost like the best to learn. So go to this website and to learn, and then there almost everything as a beginner you need to learn. It's there. And also they have really nice like benchmarking and really nice implementation. So feel free to check it out. All right, so after talk about generation task and then this reinforcement learning task, now it's the third task that are really interesting, goes beyond our classic prediction setting, supervised prediction setting, is this called the learning to learn task. So so this is a relatively vague kind of larger field, and you can almost see like whenever your formulation goes beyond the training and testing are not from the same distribution, and the task between the train and test if they changes, and then you can just claim this is a learning to learn task. So very classic are the few shots learning, zero shots learning, meta learning. So in the end, just you want to go beyond what your training data provides you. Hopefully, the learned model can generalize more beyond the training tasks. So this, if you going even one step further, kind of falls into this idea called artificial general intelligence. And some people actually criticize the current deep neural networks are only good at something called narrow AI. So they're really good at game playing, medical imaging diagnosis, or that currently people are trying to make them like autonomous car driving or just car driving. But this AGI is much more autonomous, much less supervised, much more implicit. So every task we cover so far, so there's actually a very good defined definition of the task, right? The goals. But if you think about the humans, in many situations, we are unclear about what we do. But we have a pretty good reaction, like a common sense, just this kind of implicit tasks, are much more autonomous. So people are saying like, if we truly want to make a good artificial intelligence, we should aim for AGI. But there's also some debates here, right? So what do we even mean AGI? Because intelligence, there are really different levels. Like there are maybe dog level intelligence, dolphin level intelligence, parrot level, or human level. There may be even superhuman level. So what do you even mean AGI, right? So it's a little bit vague, but it's kind of like a popular term, people trying to say like a lot in the news right now. All right, so this finished the module 2, and we're beginning module 3.
Great. So we finished the current module, and this specific ending clip is recorded after I finish all the 4 modules, and I realized my nutshell index page doesn't have the module segmentations. So here it is. So this page is better displaying how the module are related to the different elements of the nutshells, and also inside each module, and how are the topics, trend topics we selected. Okay, so great. I hope you enjoy the content and see you in the next module.